Imagine a machine so advanced, so audacious, so far ahead of its time that even today, engineers look back at its blueprints and shake their heads in disbelief. A fighter jet that was designed to take off like a helicopter, cruise at twice the speed of sound, and do it all with not one, not two, but 8 separate engines packed into a single airframe. This was not science fiction. This was not a Hollywood fantasy. This was a real program, funded by real money, built by real engineers, and nearly flown by real test pilots in the heart of the Cold War. This was the Bell XF-109, and its story is one of the most extraordinary, most overlooked, most jaw-dropping chapters in the entire history of military aviation. So sit back, because what you are about to hear will change the way you think about what human beings are capable of imagining, and what politics, money, and bureaucracy are capable of destroying. To understand why the XF-109 even existed, you have to go back to the late 1940s and early 1950s, a period of absolute electric tension in the world. The Second World War had ended just a few years before, and the world had barely exhaled before a new and far more terrifying conflict began to take shape. This was not a war fought with boots and bayonets in muddy trenches. This was a war fought in the shadows, in the skies, in the minds of generals and politicians. This was the Cold War, and it changed everything about how nations thought about military power. The Soviet Union had shocked the Western world in August 1949 when they successfully detonated their first nuclear bomb. The United States had assumed it had years, perhaps a decade, before the Soviets would reach that milestone. They were wrong, and that single explosion sent shockwaves through every branch of the American military establishment. Suddenly, the threat was not just Soviet tanks rolling across Europe. The threat was Soviet bombers carrying nuclear payloads flying directly toward American cities. The threat was real, it was immediate, and it demanded a response. The United States Air Force and the United States Navy began a frantic race to develop aircraft that could respond to this threat. They needed interceptors, aircraft that could scramble at a moment's notice, climb to extreme altitudes at extreme speeds, and engage enemy aircraft before they could deliver their payloads. But there was a problem that haunted every planner, every general, every admiral who thought seriously about this scenario. Airfields are vulnerable. Runways can be bombed. In a first strike scenario, the very infrastructure needed to launch defending aircraft could be destroyed before those aircraft ever left the ground. This vulnerability gave birth to one of the most creative and controversial ideas in the history of military aviation. What if fighter jets did not need runways at all? What if a combat aircraft could take off vertically like a helicopter, then accelerate to supersonic speeds, engage the enemy, and land vertically again in a field, on a ship, in a parking lot, anywhere? What if you could disperse your air force so completely that no enemy could ever hope to destroy it on the ground? This idea, this radical and seductive concept, became the driving force behind a whole generation of experimental aircraft programs in the 1950s, and at the very pinnacle of that ambition sat the Bell XF-109. Bell Aircraft Corporation was not a newcomer to bold ideas. This was the company that had built the X-1, the rocket-powered aircraft that Chuck Yeager had used to break the sound barrier in October 1947. Bell had a culture of risk, a culture of engineering audacity that attracted the best minds and the boldest thinkers in American aviation. When the military began searching for someone to tackle the impossible problem of a vertical takeoff supersonic fighter, Bell was ready, willing, and more than capable of stepping forward. The program that eventually produced the XF-109 concept had its roots in a military requirement that was itself almost impossibly demanding. The United States Air Force wanted an aircraft that could operate from unprepared sites. That meant no runways, no paved surfaces, just grass or dirt or gravel. They wanted an aircraft that could reach supersonic speeds, at least Mach 2, which is twice the speed of sound, roughly 1,500 miles per hour at altitude. They wanted it to carry weapons capable of engaging high-altitude bombers. And they wanted all of this in a single airframe that could be maintained and operated in austere field conditions far from major air bases. If you sat down and tried to design a more demanding set of requirements, you would be hard-pressed to come up with something more challenging. Bell's engineers dove into this challenge with everything they had. The design that emerged was unlike anything that had ever been seriously proposed for production. To achieve vertical takeoff and landing, the aircraft would need enormous amounts of thrust directed downward. To achieve Mach 2 cruise, it would need powerful jet engines oriented horizontally for forward flight. The solution Bell arrived at was breathtaking in its complexity. They would use multiple engines, some dedicated to lift, some dedicated to forward thrust, some capable of doing both. The final configuration that received serious development attention featured 8 separate turbine engines packed into a relatively compact airframe. Let that number sink in for a moment. 8 engines. A modern F-22 Raptor, arguably the most capable fighter aircraft ever built, has 2 engines. A modern airliner like a Boeing 747 has 4 engines. The XF-109 was going to have 8. And the engineering challenges this created were not merely additive, they were exponential. 8 engines mean 8 times the fuel consumption, 8 times the maintenance requirements, 8 times the potential failure points, 8 times the complexity of the fuel and hydraulic and electrical systems needed to support them. The specific engine configuration that Bell proposed evolved over the course of the program's development. The most commonly referenced design used a combination of turbofan engines for vertical lift and turbojet engines for forward propulsion. Some variants of the design called for engines mounted in rotating pods that could swivel from vertical to horizontal orientation, a concept that would eventually be proven in practice by the later Harrier jumpjet and the modern F-35B, but which in the 1950s was purely theoretical and entirely unproven at the scales and speeds being contemplated. To achieve the speeds the Air Force demanded, the XF-109 would need to push well beyond the sound barrier. Mach 2, twice the speed of sound, was the target. At that speed, the aircraft would be moving faster than a rifle bullet. It would cover a mile in less than 3 seconds. The aerodynamic challenges of sustained Mach 2 flight were, in the mid-1950s, still being actively worked out. The North American F-100 Super Sabre had only recently become the first production aircraft capable of level supersonic flight, and it barely exceeded Mach 1. Mach 2 was the domain of experimental aircraft and theoretical calculations, not operational fighters. And yet that was the target. To reach Mach 2 in a vertical takeoff aircraft, Bell's engineers had to solve problems that had never been solved before. The aircraft structure had to withstand the aerodynamic heating generated by sustained supersonic flight, temperatures that could reach hundreds of degrees on leading edges and surfaces exposed to the airflow. The fuel system had to supply 8 engines simultaneously, managing flow rates and pressures across an enormously complex network of pipes and valves. The flight control system had to manage the aircraft through regimes that ranged from a hovering helicopter to a screaming supersonic jet, 2 operating environments so different from each other that they almost seemed to demand completely different vehicles. The physical layout of the XF-109 as it was designed reflected these competing demands. The aircraft was a delta-wing design, which was the favored approach for high-speed aircraft in that era. The delta wing offered structural efficiency, the ability to store fuel, and aerodynamic properties suited to supersonic flight. The fuselage was relatively slender, housing the pilot in a forward cockpit that gave reasonable visibility. The engines were distributed through the fuselage and wing roots in a configuration that engineers had worked out would provide both the lift needed for vertical flight and the thrust needed for supersonic cruise. The inlet design for the engines was another area of intense engineering focus. Getting the right amount of air into jet engines at supersonic speeds is extraordinarily difficult. The air flowing toward the aircraft at Mach 2 is moving far faster than the engines can actually use it. It has to be slowed down before it enters the engine, a process that generates heat and requires precisely shaped inlet geometry to work efficiently across a wide range of speeds. Bell's engineers designed variable geometry inlets that could adjust their shape depending on the aircraft's speed, a sophisticated solution that added yet more complexity to an already extraordinarily complex design. The cockpit and pilot systems were similarly advanced for the era. The pilot would need to manage not just the typical demands of high-performance flight, but the additional complexity of transitioning between vertical and horizontal flight modes, monitoring 8 separate engines, managing fuel across a complex system, and executing combat maneuvers against enemy aircraft, all potentially at the same time. The cockpit design that Bell proposed incorporated instrument clusters and control arrangements specifically optimized for this multi-role complexity, with an emphasis on reducing pilot workload during the most demanding phases of flight. Now, to truly appreciate what Bell was attempting, you need to understand what vertical takeoff and landing actually means from an engineering standpoint, because it is not simply a matter of pointing engines downward. When an aircraft takes off vertically, it must generate thrust equal to or greater than its own weight. A typical jet aircraft generates thrust equal to roughly 1/4 to 1/3 of its weight during takeoff from a runway, relying on its wings to generate the lift needed to fly. A vertical takeoff aircraft needs to generate 100% of its weight in thrust, or more, just to get off the ground. For a heavy combat aircraft loaded with fuel and weapons, this is an enormous demand. The power-to-weight calculations involved in the XF-109 design were some of the most challenging ever undertaken in that era of aviation. The aircraft had to be light enough that its 8 engines could lift it vertically, but strong enough to withstand supersonic flight loads. It had to carry enough fuel to complete meaningful combat missions, but not so much fuel that it became too heavy to lift off vertically. It had to carry weapons and electronics, but every pound of those systems was a pound that had to be lifted by the engines. The engineers were constantly trading one requirement against another, squeezing every possible efficiency out of every component. The weight of fuel alone presented an almost paralyzing challenge. Jet engines are extraordinarily hungry machines, and the XF-109's 8 engines would consume fuel at a truly staggering rate, especially during vertical takeoff and landing, when all engines would be running at maximum power. The amount of fuel needed for even a short mission would itself weigh many thousands of pounds. But every pound of fuel had to be lifted off the ground by those same engines, which meant the engines had to work even harder, which meant they burned even more fuel. Engineers call this the tyranny of the rocket equation, and while it applies most brutally to space travel, it haunts any vehicle that has to lift its own fuel. The weapon systems planned for the XF-109 reflected the air defense mission it was designed to perform. The primary threat scenario was Soviet bombers carrying nuclear weapons, large, relatively slow aircraft flying at high altitude. To destroy such targets, the XF-109 would have been armed with air-to-air missiles, which were in the 1950s still a relatively new technology that the military was betting heavily upon. Guns were still considered part of the armament suite, though the prevailing thinking of the era was beginning to shift toward an all-missile armament concept, a shift that would later prove disastrously wrong in the skies over Vietnam but which dominated procurement decisions throughout the late 1950s. The radar and electronic suite planned for the XF-109 was also ambitious. Finding and engaging high-altitude bombers required airborne radar capable of looking up against the background of space, a technically demanding requirement that was pushing the limits of 1950s electronics. The fire control system had to be able to track targets and guide missiles autonomously or semi-autonomously, because at the closure speeds involved in an intercept between a supersonic fighter and a subsonic bomber, the pilot would have only seconds to identify, track, and engage a target. The electronic systems had to do much of the work automatically. What makes the XF-109 story particularly fascinating is not just the technical complexity of what Bell was attempting, but the context of the program within the broader landscape of American military aviation in the 1950s. This was an era of almost unimaginable ferment and creativity in aerospace. Every major aircraft manufacturer was proposing radical new concepts. The government was funding dozens of experimental programs simultaneously. Engineers who had grown up building propeller-driven aircraft were now designing machines that would fly faster than the speed of sound, higher than commercial airliners could dream of reaching, and in configurations that would have seemed like pure fantasy just a decade before. The competition among aircraft manufacturers for military contracts was fierce, and the XF-109 program placed Bell in direct competition with other companies proposing their own solutions to the vertical takeoff supersonic fighter requirement. Convair, Lockheed, and other established manufacturers were also working on concepts that addressed this same set of requirements. The technical approaches varied dramatically. Some companies proposed tail-sitter designs, where the aircraft would take off pointing straight up and then rotate to horizontal flight. Others proposed lift engines buried in the wings or fuselage. Bell's multi-engine approach was one of several serious contenders. The politics of defense procurement in the 1950s were, if anything, even more complex than the engineering. The service branches competed fiercely among themselves for budget and for the prestige of operating the most advanced aircraft. The Army, the Navy, and the Air Force each had their own vision of how air power should be organized and employed, and these visions often conflicted directly with each other. The XF-109 program touched on these inter-service rivalries in complex ways, because a vertical takeoff fighter that needed no airfield could potentially operate from Army positions, could launch from the decks of small Navy vessels, could be dispersed across a landscape in ways that blurred the traditional boundaries between service responsibilities. The budget battles of the 1950s were also shaped by the strategic doctrine of the Eisenhower administration, which emphasized nuclear deterrence over conventional military capability. The doctrine of massive retaliation, as it was called, held that the United States would respond to Soviet aggression not with conventional military force but with the full weight of its nuclear arsenal. This doctrine, while reassuring in its deterrent value, had complicated implications for conventional weapons programs like the XF-109. If nuclear weapons were going to win any future war quickly and decisively, why spend enormous sums developing a sophisticated conventional fighter aircraft? These budget pressures meant that even programs that were technically promising faced constant scrutiny and the threat of cancellation. Engineers working on advanced aircraft programs learned to navigate not just the technical challenges of their designs but the political challenges of justifying their programs to increasingly skeptical budget officers and congressional committees. The language of defense procurement required a peculiar blend of technical specificity and political persuasion, and programs that could not master both faces of that challenge were vulnerable regardless of their technical merit. Bell's engineers and managers understood this reality, and they worked hard to position the XF-109 as essential to national defense in a way that would survive budget scrutiny. The arguments they made were compelling on their surface. In a nuclear war, airfields would be among the first targets struck. An air force that depended on fixed airfields was an air force that could be neutralized in the opening minutes of a conflict. A vertical takeoff force dispersed across thousands of locations was effectively invulnerable to any conceivable first strike. The logic was sound. The question was whether the technical challenges could be solved within a budget that the government was willing to sustain. As Bell pushed forward with the XF-109 design in the mid-1950s, the program began generating the kind of attention that advanced aircraft programs attract. Aviation enthusiasts, journalists, and military analysts began to take notice of what Bell was proposing. The concept was audacious enough to capture the imagination, and in an era when American technological optimism was at a historical peak, the idea of an 8-engine Mach 2 vertical takeoff fighter did not seem impossibly fantastic. It seemed like exactly the kind of bold leap forward that American industry was capable of delivering. The technical review processes that military programs went through in this era were rigorous, and the XF-109 faced skeptical questions from experienced engineers who understood the depth of the challenges involved. The engine swiveling mechanisms, if used, would have to operate reliably under enormous loads and extreme temperatures. The flight control system would have to manage the transition between vertical and horizontal flight smoothly enough that a pilot could actually execute it under combat conditions. The structural design would have to be light enough to meet the weight targets while being strong enough to survive the loads of supersonic flight. Each of these challenges was real, significant, and would require substantial development work to solve. But Bell had a track record that gave their proposals credibility. The X-1 had broken the sound barrier. The Bell Helicopter Division had become a leader in rotary wing aviation. The company had demonstrated repeatedly that it could take on challenges that other manufacturers considered impossibly difficult and find practical engineering solutions. When Bell said the XF-109 could be built, it was not an empty boast. It was the assessment of engineers who had done the calculations and believed the physics would allow what they were proposing. The role of the Cold War's strategic urgency in driving the XF-109 program forward cannot be overstated. The late 1950s were a period of intense anxiety about Soviet military power. The Soviets had launched Sputnik in 1957, demonstrating a space launch capability that implied an intercontinental ballistic missile capability. The so-called missile gap, the fear that the Soviets had more and better ballistic missiles than the United States, dominated political debate. In this environment of strategic anxiety, arguments for bold technological investments in military capability found receptive audiences. The XF-109 program benefited from this environment even as it was also threatened by it. On one hand, the strategic case for a dispersible supersonic fighter force was compelling precisely because the vulnerability of fixed airfields was a real and acknowledged problem. On the other hand, the rise of ballistic missiles as the primary nuclear delivery system was beginning to shift attention and budget away from manned aircraft programs entirely. Why build sophisticated fighters to intercept bombers when the real threat might be missiles that no fighter could intercept? This strategic shift created an existential challenge for the XF-109 program that was ultimately more dangerous than any technical obstacle. The program's entire rationale rested on the assumption that manned nuclear bombers would remain the primary Soviet strategic threat. If that assumption was wrong, if ballistic missiles became the dominant threat, then the elaborate and expensive solution that the XF-109 represented became irrelevant. Program managers at Bell and their supporters in the military had to argue not just that the XF-109 was technically feasible and cost-effective, but that the strategic threat it addressed was real and enduring. That was an argument that became progressively harder to make as the 1950s advanced. The actual development timeline of the XF-109 program went through several distinct phases, each characterized by a particular configuration and set of technical priorities. In the earliest phase, Bell explored a wide range of possible solutions to the vertical takeoff supersonic fighter requirement, considering everything from pure helicopter-like lift systems to thrust augmentation devices to the multi-engine configurations that eventually dominated their thinking. This exploratory phase involved wind tunnel testing, computational analysis, and detailed engineering studies that helped narrow the design space. As the design converged toward the multi-engine configuration, Bell invested heavily in component development and testing. Individual engine installations were tested to understand how the engines behaved when arranged in the close proximity that the design required. Structural tests validated the analysis of how the airframe would respond to the loads of supersonic flight. Wind tunnel models were built and tested to understand the aerodynamic behavior of the configuration across the wide speed range from hover to Mach 2. The wind tunnel tests were particularly revealing and in some respects sobering. The aerodynamic interaction between the lift engines and the airframe during hovering flight created complex flow patterns that were difficult to predict analytically and had to be measured experimentally. The jet exhaust from engines pointed downward created a ground effect that changed the aircraft's behavior as it approached the ground, an effect that could make landings unpredictable and potentially dangerous. Managing these effects required careful attention to the positioning of the lift engines and the design of the exhaust ducting. The transition from vertical to horizontal flight, what engineers called the conversion maneuver, was also explored extensively in both analysis and wind tunnel testing. This maneuver, which would take the aircraft from hovering on its lift engines to accelerating through the transonic regime on its cruise engines, was one of the most technically demanding aspects of the entire design. The pilot would have to manage the throttling of multiple engine groups, while maintaining control of the aircraft as its aerodynamic characteristics changed dramatically with speed. Modern aircraft like the F-35B and the Harrier have demonstrated that this transition can be accomplished safely and reliably, but the engineering work needed to reach that point was enormous, and in the 1950s none of it had been done yet. Bell's engineers were working from first principles, developing the analytical tools and the test methodologies that would be needed to validate their approach, because those tools and methodologies did not yet exist. The pilot training implications of the XF-109 were also a subject of considerable discussion within the program. Flying this aircraft would have required skills that no existing pilot training program produced. Converting between vertical and horizontal flight modes, managing 8 separate engines, operating in the extreme performance envelope that the design called for. All of these capabilities would have required an entirely new approach to pilot training and selection. The aircraft would have been demanding beyond anything that Air Force pilots of the era had experience with, and the accident rate during the development and early operational phases would almost certainly have been significant. This concern about pilot workload and safety was not unique to the XF-109. All high-performance aircraft of the era were dangerous, and accidents were an accepted, if mourned, cost of pushing the boundaries of aviation technology. The 1950s were a decade of extraordinary loss among test pilots and even operational pilots as the services worked to master the new generation of jet aircraft. But the XF-109's unique complexity meant that the demands it would place on its pilots went beyond even the high standard already required for frontline jet fighters. The maintenance implications of the design were equally challenging. 8 engines do not merely require 8 times the maintenance of a single engine. The close proximity of the engines within the airframe makes each one more difficult to access. The complex ducting and transition mechanisms add maintenance items that do not exist in simpler aircraft. The specialized skills required to maintain such a system would have required a significant expansion of the technical training pipeline and a dedicated logistics infrastructure. In the real-world environment of dispersed operations from unprepared sites, which was the whole point of the design, maintaining this level of complexity would have been extraordinarily challenging. These practical operational concerns were raised by experienced military officers who understood from hard experience how difficult it is to maintain advanced aircraft in field conditions. The history of military aviation is full of aircraft that performed brilliantly in peacetime demonstrations and performed poorly in actual operational service because their maintenance demands could not be met under the stresses and constraints of real military operations. The XF-109's complexity made it particularly vulnerable to this critique. Bell's engineers responded to these concerns with designs that tried to minimize maintenance demands, grouping components for easy access, standardizing parts across engine types where possible, and designing the aircraft for what they called line maintenance, the kind of quick turnaround servicing that operational units needed to keep aircraft flying at high rates. But the fundamental complexity of the design imposed limits on how far these improvements could go. There was simply no way to make 8 engines as simple to maintain as 1 or 2. The cost implications of all this complexity were staggering by the standards of the era. Aircraft procurement costs in the 1950s were already a source of intense congressional concern. The new generation of jet aircraft was dramatically more expensive than the propeller-driven aircraft they replaced, and the rate at which costs were escalating alarmed budget planners. The XF-109's complexity promised to push costs even further, at a time when the Air Force was already struggling to justify its procurement budget. The economic argument against the XF-109 was simple and powerful. For the cost of one XF-109, you could buy several conventional supersonic fighters. Those conventional fighters would individually be less capable in the vertical takeoff role, but they could still perform the air defense mission from conventional airfields. And if you spent the money saved on hardening those airfields, or on building more dispersed conventional airfields, you might achieve a comparable level of survivability at lower cost. This argument, which was made by critics of the program, was never definitively answered. As the 1950s drew toward a close, the XF-109 program found itself facing an increasingly hostile environment. The Eisenhower administration's defense budget philosophy emphasized economy and fiscal discipline alongside nuclear deterrence. Conventional military programs that could not demonstrate clear cost-effectiveness were vulnerable. The XF-109's enormous development costs and the uncertainty about whether its technical challenges could actually be solved within budget made it a tempting target for budget cutters. The program also faced competition from other approaches to the dispersed basing problem. Some military planners argued that the answer to airfield vulnerability was not vertical takeoff aircraft but rather supersonic aircraft that needed very short runways, so-called STOL or short takeoff and landing aircraft, which were simpler and cheaper than true vertical takeoff designs. Others argued for underground and hardened airfield facilities that could survive nuclear attack. The XF-109's proponents had to argue not just that their approach was feasible, but that it was better than these alternatives. The debate over alternative solutions to airfield vulnerability was never resolved in favor of any single approach, which itself was problematic for a program as expensive and risky as the XF-109. When military planners cannot agree on whether a capability is truly necessary, programs that represent the most expensive and most technically risky approaches to achieving that capability tend to lose out. The XF-109 was the most extreme solution to a problem whose urgency was itself in dispute. The program's fate was also affected by changes within Bell Aircraft itself. Corporate priorities, management changes, and the demands of other programs all influenced how much energy and resources Bell could devote to the XF-109. A program of this ambition required sustained institutional commitment over many years, and sustaining that commitment through the inevitable technical setbacks and budget battles required leadership that was deeply invested in the program's success. When we look at what was actually built and tested in connection with the XF-109 program, we need to be precise about what reached hardware and what remained on paper. Bell did build and test aircraft related to the vertical takeoff fighter concept, and these tests generated valuable technical knowledge. But the full XF-109 as envisioned never flew. The program was canceled before a prototype of the complete design was built and tested. This outcome, frustrating as it must have been for the engineers who devoted years to the program, was not unusual for advanced experimental aircraft programs of the era. The majority of the remarkable aircraft concepts generated during the 1950s never progressed beyond the design and early development stages. The technical risks were simply too high, the costs too uncertain, and the competing priorities too pressing for most programs to survive the full development cycle to operational aircraft. But the cancellation of the XF-109 did not mean that the work done on the program was wasted. In military aviation, canceled programs frequently produce technical knowledge, engineering methodologies, and trained personnel that feed directly into subsequent successful programs. The work Bell did on vertical takeoff dynamics, on multi-engine management systems, on the aerodynamics of aircraft transitioning between vertical and horizontal flight, all of this knowledge contributed to the broader base of understanding that eventually made aircraft like the Harrier and the F-35B possible. The legacy of the XF-109 program is therefore not measured solely by what it produced in hardware, but by what it contributed to knowledge. The engineers who worked on the program learned lessons about what was and was not achievable within the technology of the era. They developed analytical tools and testing methodologies that advanced the entire field of vertical takeoff aircraft design. They identified the specific technical problems that needed to be solved before vertical takeoff supersonic fighters could become reality, and in doing so, they pointed the way for later programs that did eventually achieve at least part of what the XF-109 had attempted. The comparison between the XF-109 and later vertical takeoff aircraft is instructive. The British Hawker Siddeley Harrier, which first flew in 1967 and entered service in 1969, achieved the vertical takeoff mission but at a very different performance level. The Harrier was subsonic in operational configuration, capable of brief supersonic dashes but not sustained Mach 2 cruise. It used a single engine with swiveling thrust nozzles rather than multiple separate engines. A simpler and more practical approach that sacrificed some performance for reliability and maintainability. The Harrier succeeded in part because it made exactly the kind of pragmatic compromises that the XF-109 program had been unwilling to make. The F-35B, which entered service more than half a century after the XF-109 was being designed, achieves short takeoff and vertical landing capability with a single engine and a shaft-driven lift fan. It is supersonic, though not at Mach 2. It represents the closest thing yet achieved to the XF-109's vision of a supersonic vertical takeoff combat aircraft, but it achieves that vision with technology that simply did not exist in the 1950s. Modern computers manage the complex control systems that the XF-109 would have required. Modern material science produces structures that are stronger and lighter than anything available to Bell's engineers. Modern engine technology achieves thrust-to-weight ratios that would have seemed miraculous to 1950s designers. The XF-109 was not wrong in its vision. It was simply ahead of the technology of its time. The requirements it was designed to meet were real, the strategic logic behind those requirements was sound, and the engineering concepts the Bell team developed were, in many ways, prescient. What the program lacked was the technology to execute those concepts within cost and schedule constraints that a 1950s defense budget could sustain. This pattern of visionary aircraft programs that were correct in concept but premature in execution runs throughout the history of military aviation. The German Messerschmitt Me 262 was the world's first operational jet fighter, but was introduced too late and in too small numbers to change the outcome of the Second World War. The Northrop YB-49 flying wing bomber anticipated the B-2 Spirit by decades, but was cancelled for reasons that mixed technical problems with inter-service politics. The North American XB-70 Valkyrie was an extraordinary achievement in aeronautical engineering that was rendered obsolete by the very ballistic missile technology that was then reshaping the strategic landscape. The XF-109 belongs to this tradition of magnificently conceived, technically brilliant programs that the world simply was not ready for. It represents a moment in history when American engineering ambition reached so far ahead of available technology that the gap could not be bridged within the constraints of real-world program management. And yet, the reaching itself mattered. The knowledge generated, the problems identified, the solutions partially developed, all of these contributions rippled forward through time and eventually bore fruit in aircraft that would have amazed even the optimistic engineers who worked on the XF-109. The human side of the XF-109 story deserves attention as well. The engineers who worked on this program were extraordinary individuals, people who had grown up building conventional aircraft and were now being asked to solve problems at the very frontier of human knowledge. They worked with slide rules and mechanical calculators because digital computers were in their infancy. They designed structures using analytical methods that required extraordinary skill and experience to apply correctly. They tested their designs in wind tunnels that could only approximate the complex real-world conditions the aircraft would encounter. These engineers brought to their work a combination of deep technical knowledge, practical engineering judgment, and genuine passion for the challenge they faced. Aviation history is full of accounts by engineers who worked on great aircraft programs and who describe the experience with an intensity and a pride that decades cannot diminish. The XF-109 program was that kind of experience. Even though the aircraft never flew, the people who worked on it understood that they were grappling with some of the hardest problems in engineering, and that understanding gave the work a significance that went beyond the program's ultimate fate. The test pilots who were associated with the XF-109 program, who might have flown the aircraft had it reached the prototype stage, represent another dimension of the human story. Test pilots of the 1950s were a remarkable breed. Men who combined exceptional flying skill with engineering knowledge deep enough to evaluate and report on the characteristics of aircraft that had never been flown before. They accepted risks that would be considered unacceptable today, because the state of knowledge about aircraft behavior was so incomplete that dangerous surprises were inevitable. Flying an 8-engine vertical takeoff aircraft for the first time would have been an act of extraordinary courage. The culture of military aviation in the 1950s celebrated this kind of courage while also recognizing its costs. The decade saw the loss of many exceptional test pilots and operational flyers as the services pushed the boundaries of performance. Each loss was mourned, and each loss also generated knowledge about what had gone wrong and how future designs could be made safer. The XF-109 program, had it progressed to flight testing, would almost certainly have contributed to this tradition of learning through loss. Looking at the XF-109 from the vantage point of the present, several aspects of the program stand out as particularly remarkable. First, the boldness of the original concept. In an era when vertical takeoff aircraft barely existed and supersonic fighters were just entering service, proposing a vehicle that would do both simultaneously was an act of extraordinary creative ambition. The willingness of both Bell's engineers and their military customers to seriously pursue such a concept says something important about the spirit of that era. Second, the depth of the engineering analysis that went into the program. Despite the fact that the XF-109 never flew, It was not a superficial concept. Bell invested serious resources in working through the detailed engineering challenges, and the technical documentation the program generated reflects genuine analytical depth. This was not a paper airplane in the pejorative sense. It was a serious engineering effort that engaged honestly with the formidable challenges involved. Third, the prescience of the program's core insight. The vulnerability of fixed airfields to nuclear attack was a real strategic problem, and the vertical takeoff solution to that problem was conceptually correct, if technically premature. Decades later, when the technology had caught up with the concept, vertical takeoff aircraft did indeed enter service with air forces and navies around the world, validating the strategic logic that had motivated the XF-109 program. The story of the XF-109 is also a story about the relationship between technology and strategy, about how military requirements shape engineering ambition and how engineering possibility, or the lack of it, constrains strategic options. The 1950s were a period when technology was advancing so rapidly that the gap between what was strategically desirable and what was technically feasible was constantly shifting. Programs like the XF-109 existed in that gap, pushing against the boundary of the possible with the energy of necessity and the force of imagination. The cancellation of the XF-109 did not eliminate the strategic requirement it was meant to address. Airfield vulnerability remained a concern throughout the Cold War and continues to be a concern in contemporary military planning. The solutions that were eventually adopted to address that concern, hardened airfields, dispersed basing, short takeoff and vertical landing aircraft, underground facilities, all of these reflected the same strategic logic that had motivated the XF-109. The problem was real. The question was always which solution was most cost-effective given the technology available at any given moment. In the broader context of Cold War aviation history, the XF-109 occupies an important place as one of the most ambitious aircraft programs ever seriously pursued by a major manufacturer. It pushed the boundaries of what was considered possible, generated important technical knowledge, and anticipated capabilities that would not be achieved until decades later. Its cancellation was a disappointment for the engineers and military officers who believed in it, but the knowledge it generated lived on and contributed to the eventual achievement of the capabilities it had sought to create. The aircraft that did eventually achieve supersonic performance and vertical takeoff or landing capability, the F-35B being the most prominent current example, stand as vindication of the XF-109's fundamental vision. The fact that it took 60 years and an enormous advance in technology to achieve what Bell was proposing in the mid-1950s speaks to how far ahead of its time the XF-109 actually was. This was not a program that failed because its vision was wrong. It was a program that was canceled because its vision was right, but the technology to achieve it did not yet exist. Today, as we look back at the XF-109 from a world where vertical landing rockets are routine, where fly-by-wire flight control computers manage aircraft dynamics in ways that 1950s engineers could only dream of, where engine technology routinely achieves thrust-to-weight ratios that would have seemed miraculous to Bell's design team, the XF-109 looks less like a failed program and more like a message from the future, a message that was received by the present only after a long delay. The engineers who drew its blueprints were not building an aircraft for 1960. They were building an aircraft for the 21st century, and they were doing it with the tools of 1955. That gap between ambition and capability, between what the mind could conceive and what the hands could build, is one of the most human things about the XF-109 story. It is a story about people who refused to accept the limitations of their time, who pushed against those limitations with everything they had, who fell short but in falling short pointed the way for those who would come after them. In that sense, the XF-109 is not just an aircraft program. It is a testament to the enduring human drive to transcend what is possible today in pursuit of what might be possible tomorrow. The men who worked on the Bell XF-109 are mostly gone now. The slide rules and drawing boards they used have been replaced by software and computers. The Cold War that made their work urgent has ended, replaced by different threats and different strategic challenges. But the spirit that animated their work, the conviction that no problem is too hard, no challenge too formidable, no vision too bold, That spirit is as alive today as it was in the drafting rooms of Bell Aircraft in the mid-1950s. And it is a spirit worth honoring and remembering, not just because of what it built, but because of what it attempted. So the next time you see a fighter jet roar across the sky, or watch an F-35B lower itself onto a carrier deck with the delicate precision of a hummingbird, take a moment to think about the Bell XF-109. Think about the 8 engines, the Mach 2 target, the dream of a fighter that needed no runway. Think about the engineers who drew those blueprints and ran those calculations and argued those technical points with total conviction that they were onto something important. They were right. They were just right too early. And that, in the end, is perhaps the most important lesson that the XF-109 has to teach. In aviation, as in so many fields of human endeavor, being right too early can be just as challenging as being wrong. The vision matters. The technology to realize the vision also matters. And sometimes the most courageous thing a person can do is to push as far as possible toward a vision that will only be fully realized by someone else, at some other time with some other set of tools. The Bell XF-109 pushed that far. And the world of aviation is better for it.